Hi everyone! In this video we're going to look at the variables that describe a gas and how those variables relate to one another. So gases can be described with respect to the amount, that is the moles of particles, and we can describe a gas with respect to its volume. Gases are unique in that they expand to fill the space that they're provided. So whatever the size of your container, those gas molecules will spread out to fill that container completely. And pressure is another variable that can be used to describe a gas. We know that pressure is due to molecular collision. So these gas particles are moving very fast. They're bouncing off the walls of the container, or the atmospheric pressure, for example, is the same idea. These collisions cause some kind of pressure. And the final variable that we can use to describe a gas is its temperature. So we can use kinetic molecular theory to explain how all of these variables affect each other, and we'll tie all that together in this video. Through experiments and observations, these four variables that describe a gas are found to be related to one another. And these relationships are described by what we call gas laws. And a law in science is something that is based on experimental observation. So we've heard of the law of conservation of mass, which says that the mass before a chemical reaction is equal to the mass after a chemical reaction. That's something that you observe through an experiment. And that's all that a law is. It tells you a statement that describes your results from experiment or observations that you made. And a theory, on the other hand, will explain the law. So we can use kinetic molecular theory to explain why these gas laws hold true. So the four gas laws that we're going to look at are Boyle's law, Charles' law, Avogadro's law, and then the lesser known Gay-Lussac's law, or sometimes it's known as Montan's law. And I won't expect that you know the names of these relationships, but simply the relationships themselves. So let's start with Boyle's law. Boyle's law describes the relationship between volume and pressure. Let's make some observations to see if we can come up with the relationship of volume and pressure. Let's take this potato chip bag. It is at sea level in this first image. Now let's look at an image of that same potato chip bag at a higher elevation. What observations can we make about this bag? Well, it should be obvious that the volume of that bag has changed. So what happened to cause the volume of the bag to change? It's still sealed. There's no more or less gas in there. The temperature, let's say, is the same, so no change in temperature. But we know that there is a difference with respect to the altitude in pressure. So as we go to higher altitudes, we experience lower pressures. So the pressure has decreased and the volume of that chip bag has increased. So the relationship is inverse. As the volume increases, the pressure decreases, or vice versa. As my pressure decreases, my volume increases, which is what we observed in this experiment. Let's look at a graph of volume plotted against pressure. And here we see that that relationship is holding true, that as my volume decreases, the pressure increases, but it's not a linear relationship, okay? So if we write it as volume is proportional to 1 over pressure, and likewise we could write pressure is proportional to 1 over volume, we could plot these relationships. So a pressure versus 1 over V plot is going to look something like this. And here we do see a linear line representing this trend at various temperatures. We can use these relationships to solve what are known as change of state problems. So if we have a situation before a change occurs and we have a situation after now, we can calculate the change in pressure or change in volume based on what kind of change occurred. So in order to do that, we have to come up with a mathematical equation. So if we take this relationship of volume and 1 over pressure, we can replace that proportion symbol with a constant. So volume is equal to a constant times 1 over pressure. And if this is the first scenario, we can define this constant as P1 V1 equals K. And if we have a second scenario after some change has occurred, we could say that the second situation, P2 V2, is equal to the same K, right? This constant is in fact a constant. So since these two K values are equal, we can derive this equation P1 V1 equals P2 V2. And this is what you may typically see as Boyle's law, describing the relationship of pressure and volume. Now, we'll see that we don't need to memorize each individual relationship because we will be able to combine all of these relationships into the ideal gas law. Thinking about Boyle's law with respect to kinetic molecular theory and how molecules are in constant motion, and those molecules are colliding with not only each other but the walls of a container, exerting some pressure. As that volume decreases, those particles are traveling shorter distances, and so they'll have more collisions per unit time. More collisions means a higher pressure. So we can, again, explain the law by using the theory. Avogadro's law relates the variables of moles and volume. This one should be quite obvious. Think about blowing up a party balloon. You blow in some amount of air, the volume increases. If you put more air in, that's more moles of air, molecules, the volume's going to increase. So as N increases, volume increases. And that means that N is directly proportional to V. So we can set up a equation here where N is equal to K times V, much like we did for the pressure-volume relationship. And if we have a before and an after, we can derive a relationship here that can be used to solve, again, change of state equations. So we have N1 over V1 equals N2 over V2. And this is Avogadro's law, where the other two variables, pressure and temperature, must be constant for this to hold true. Let's take a look at a graphical representation of this law. We see that volume is plotted on the y-axis and moles on the x-axis, and it is a linear relationship. As the number of moles increases, my volume will increase. And the volume depends only on the moles of gas, right? So 1 mole of gas is going to occupy the same volume no matter what that gas's identity is. So something very light like helium is going to occupy the same volume as 1 mole of a heavier gas like argon, okay? So the volume is dependent only on the number of moles, not mass. It is true that 1 mole of helium will weigh less than 1 mole of argon, but they will occupy the same volume of space. Connecting Avogadro's law to kinetic molecular theory allows us to explain this observation. So KMT says that molecules are in constant motion, colliding with one another in the walls of the container, and those collisions cause the pressure that we know. So if the temperature is constant, the molecules are traveling at the same speed, so if we put more molecules into a container, in order for the pressure to remain constant, the volume of that container must increase. Charles' law describes the relationship of volume and temperature. And this relationship can be observed on, say, a cold day. Let's say you take a balloon from your house and you take it outside. That balloon will get smaller. And so why does that balloon get smaller? So as the temperature decreases, the volume decreases. So that, again, this is a direct relationship that volume is proportional to the temperature as long as pressure and moles are constant. Okay? We can write this as V equals K times T. So V over T is equal to K. Again, thinking change of states, the volume and temperature before must be equals to some constant, which the volume and temperature after will be equal to the same constant as well. So combining these two, we get V1 over T1 equals V2 over T2. And again, we don't have to memorize all of these equations because the ideal gas law will eventually show us how these are all related to one another. Look at this Charles law plot including volume and temperature. We have volume on the y-axis and temperature on the x-axis. We see a linear relationship between the volume in liters and the temperature in degrees Celsius. Now, which of these statements can best describe the relationship between volume in liters and temperature in degrees Celsius? You may have been tempted by or chosen answer A here, where it says volume over temperature is equal to a constant K. Well, this is actually not true when we're talking about degrees Celsius. Look at the plot. We have, let's say, a volume of 15 liters over the temperature at that point. I'm looking at the blue line. The temperature at that point is 100 degrees Celsius. And that would equal some number, right? Then if we say, pick another point on this curve, let's look at the blue line again, volume of 20 liters and a temperature of 200 liters, temperature of 200 degrees Celsius. This isn't going to work out to be the same number as that, is it? So it's not true that volume over temperature equals a constant K. Okay? Now, the second option, B, volume is equal to K over T, is not true either. That would show an inverse relationship between volume and temperature, which is clearly not true based on the plot that we see there. This would imply that as volume increases, temperature decreases, which is not the case. And then the final answer, option C, is if the temperature is doubled, the volume does not double. So if we look at the temperature, 100 to 200 degrees Celsius, on, say, the blue line, the volume is 15 degrees, and then at 200 it's 20 degrees. Is that double? No. So that is the true statement here, that the volume does not double when the temperature doubles in degrees Celsius. Now this does hold true in Kelvin. So the volume is proportional to the temperature in Kelvin. It's proportional to temperature, but we can only compare the absolute temperature on the Kelvin scale. The final law that we're going to look at relates the variables of temperature and pressure. This is known as Gay-Lussac's law or Amonton's law. So you've observed this relationship before as well. Have you ever microwaved food in a closed container? You're increasing the temperature, and then you open it up once it's finished heating, and you have to pry that lid off, or you have to, or you hear a popping sound because the pressure increased within that container. Another example is that you take your milk out of the fridge in the morning, you let it sit on the counter for a few minutes, you twist off the cap and you hear the pop because the pressure had increased, and then that release of the pressure makes the audible sound. Okay? So as the temperature increases, the pressure increases. Connecting this to KMT should make sense, right? As the temperature increases, the kinetic energy of the molecules is increasing. So the speeds are increasing, which is going to result in more forceful collisions, which will be causing a higher pressure. All right, so carrying out the same kind of process, temperature is equal to some constant times the pressure. T1 over P1 equals K. In another scenario, T2 over P2 would equal the same K. So putting this together, we get the relationship between temperature and pressure at constant moles and constant volume. Okay, so we're talking rigid containers here that can't easily expand or contract like a balloon could, for example. The ideal gas law takes these three core relationships, Boyle's law, Charles' law, and Avogadro's law, and relates them through the ideal gas law. So combining this, we can say V is proportional to T times N over P. And if we rewrite this, volume equals some constant, R, times T times N over P, and rearrange, we get PV equals nRT. And this is my ideal gas law, showing me the relationship between pressure, volume, and temperature in one simple equation. And if we're thinking about change of state problems, right, we can rearrange this and say P1 V1 over N1 T1 equals R. So if we have two scenarios, P1 V1 over N1 T1 would be equal to P2 V2 over N2 T2. And from this, we can derive any of the three gas laws, right? When moles and temperature are constant, they're going to cancel out from this equation. So we'll have PV equals PV, right? If volume and temperature are varying while pressure and moles are held constant, we have Charles' law, volume and temperature relationship. And if my pressure and temperature are constant, the volume and moles are varying here. So we can plug in all the numbers into this equation and solve it the same way that we would if we used individual Boyle's, Charles', or Avogadro's laws. So simply using the ideal gas law would allow us to be able to solve those change of state problems by plugging in the appropriate numbers into this equation. Keep in mind that the temperature has to be in Kelvin when you're solving these gas law problems. And I will also point out that my R is a value that is on your data sheet. So R is equal to 0.08206 liters times ATM per mole Kelvin. The units here on R can be used as a clue as to the units that you need to use for the variables in this equation. So pressure in ATM, volume in liters, N in moles, T in Kelvin. As long as you use the appropriate units, they will cancel and you'll be left with the unit that you are solving for. Thanks for watching this video on the gas laws. Let me know if you have any questions, and we'll see you next time.